So let's first understand what internal forces do when they interact with a rectangular corner. And to talk about that, let's first draw a frame. So I'm going to draw a regular frame here on my canvas. And I'm, of course, exaggerating a little bit. And keep in mind that we always had horizontal members before. Now we are dealing with horizontal and vertical members. So we are familiar with the reference fiber. And now completely randomly, or for no good or better reason or worse reason, I will put the reference fiber on the inner side of the frame. But nobody would stop me from doing that on the outer side of the frame. This is just by choice. However, this reference fiber that I just included defines where the positive and negative side of the frame is, as we will see in a second, or as we have seen before actually for our regular beams. And now, as always, I will release the internal forces at that location by cutting the frame. And to do that, I'm going to eliminate some parts here. And I can do the same thing on the vertical components, just so that I can release my internal forces. So the first thing I'm going to do is I'm going to cut the system. And I do that everywhere. Cut, cut. And to make my life easier, I'm also going to name these members. So I'm going to call this member 1, member 2, member 3, and member 4. I don't bother about the ones on the bottom. Those are not relevant for us right now. However, I'm going to use them to tell the entire story. So the first and easiest thing to do is probably to focus on member 2 and 3. And in member 2, I have a right side cut, so I can just use my regular study card that we developed in a lecture before, in which I bring in my internal forces. And those internal forces are the moment, the shear force, and the normal force. And as before, the shear force has to go down, the normal force has to go to the right, and the moment has to turn counterclockwise. And this is on account of the reference fiber being on the bottom here. So now same logic applies to the left cut in member number 3. So I'm going to bring in my internal forces here. But be careful now, because it's a left cut, therefore my forces are actually opposite to each other. Otherwise they could not balance what happens in member number 2. So actually member 2 and 3 are one member, but I cut them in half. And they have to balance, of course, at that cut. Otherwise the system could not be in equilibrium. So now for the first time we're actually dealing with vertical members here, member 1 and member 2. And again, the reference fiber tells us what to do next. So keep in mind that the reference fiber pretty much tells us the direction of the positive and negative y-axis, but also tells us where x is positive. So for example, if I look at member 2 here, the x-axis is positive to the right, and then the y-axis would be positive upwards. The same is true if I shift my logic by 90 degrees here for member number 1. So the axis of the member actually becomes a vertical direction, and positive and negative y direction is to the left and to the right of this member. So let us introduce our internal forces at that cut now. So it's a left cut in this case, so my moment is clockwise. My shear force has to go up, which in this case is actually to the left, and my normal force has to go down. Which, of course, normal force, once again, is normal to the cross-section of the member actually, so it's in line with the axis of the member, and therefore it's going down in this case. Now, if I look at the bottom part of that, of course, it's opposite because it's a right cut. So I would have a moment here, I would have a shear force here, and I would have a normal force that's going up. But we're not caring about these members right now, or about those components right now. On the other side, for member number 4, it's a similar story, but I have to use my study card again with those internal forces. So I'm gonna bring in my internal forces like that, the moment being counterclockwise, the shear force pointing to the left in this case, or down relative to the reference fiber, and the normal force going down or in line with the reference fiber but away from the cut. And now we see something very specific here because we're dealing with right-angled corners. So this is very specific, and we can memorize, or we can understand, that the shear force, for example, acts relative to the normal force. So the normal force here, this normal force, is turning into the shear force at the 90-degree corner. So whatever force the normal force takes up here has to be balanced by the shear force in the corner. And I want to point out again, this corner can be like as tiny as like a millimeter only here, and this picture would still be true. And in that case, this force, the normal force, has to balance the shear force at that corner. But this is only true because we're dealing with a 90-degree corner. And I can do the very same thing with my normal force here. My normal force has to balance my shear force here. Or not balance, but they have to interact with each other, if you will. And the very same thing is, of course, true again on the other side. So maybe I can do a better job showing it this time. So the shear force here has to go and interact with the normal force. And the shear force at member 4 has to interact with the normal force at member 3. So that is something we can memorize, that at 90-degree corners, the shear force and the shear force and the normal force interact with each other, right? So at 90-degree corners, V turns into N, and N turns into V. Careful, however, because the moment does not change at the corner, right? Because the moment only turns about a point, and it doesn't matter if it turns, clockwise or counterclockwise, the value has to stay the same. And by the way, the same is also true for the shear force and normal force. Like the positive and negative is only defined by the reference fiber. So if the reference fiber here, for example, would be on the other side, then the sign of course changes, but physically it's still true that whatever is acting vertical in this member is acting perpendicular to this member. And so the shear force and the normal force in right-angled corners have to counteract each other and balance each other. Whereas the moment turns about a point, so you can think of it as this moment turning about this point, and this moment turns about that point. So the value stays the same at the corner, but you will see that when we actually run a real problem. So for now, it's important that we understand that the shear force and the normal force actually interact with each other in a particular case of a 90-degree corner. This is very unique to a 90-degree angled system. And so that concludes our 4.9.1 internal forces at rectangular corners. So we are almost ready to solve a problem, but remember that we also want to talk about hinges